Good morning, everyone. This is Jim Chastain with EasyPower. Appreciate your joining us this morning. And this is actually one of my favorite presentations because it involves a fair amount of interaction with the audience, both based upon dialogue that we've had in the past, questions that have come in on different projects, and feedback as much as anything else as a suggestion on how to improve, especially if you're a beginner in Arc Flash. So welcome everyone to the presentation, and this is actually part 2 of what we have done in the past. In the previous broadcast that was about a month ago, we covered the first half of the list of 10 most common errors. And just as a way of previewing, here's what the first 5 errors were. Very frequently, a first-time user of the tools has a tendency to start too large with the one-line diagram construction, and as a result, they have a large drawing with multiple errors and not quite sure where to start. And so what I recommend, especially for a very first-time beginner, is to start with a very simplistic one-line diagram that shows your source, whether it's utility, batteries, or generators, and then a single connection down to the lowest load that you need to label, and make sure that you're aware of what the mechanics of the tool and the data that's required to generate the outputs that you want. And again, this is for a beginner. It's not bad advice for someone even on their maybe 10th or 20th study if they haven't done one recently that could be of a different style of system. So anyway, the next most common error is inadequate data entry. Once you go to do Arc Flash calculations and then you look at the Arc Flash hazard spreadsheet, the most common error message is no valid device found. And so that ends up being problematic. And again, it would have been uncovered if you'd have had started initially. So these two errors go hand in hand. A third question, and frequently this comes up in initial studies, and that is, should we expect to see very elevated incident energy levels on 208 volt systems? And this goes to the fact that the IEEE guidelines and NFPA 70E both refer to the fact that below 125 kVA sourced and voltages less than 240 volts, there's a very low possibility of Arc Flash blast or instant Arc Flash hazard. And so it's the results are conservative based upon using the IEEE model. So the question is, if you see large elevated energies, there are basically 2 approaches. One is they could be realistic insofar as if the energy level supplying that voltage is greater than 125 kVA, I would be careful how I tweak the calculations before I understood the currents involved. And there's adjustments in the tool that allow us to limit the amount of time the calculations are conducted if we are less than 125 kVA supply. Pointed out last time that there's the ability to amplify or better describe what type of bus, even if we're drawing in just a plain vanilla bus, and how we categorize that bus will affect the type and rating in terms of the dimensions, the air gap dimensions that are used in the Arc Flash calculations. So frequently, that's an area that people overlook, in part because the tool doesn't require it as a condition of just constructing the one line. And so this is, again, something to look at and review as you're kind of becoming more mature and using the tools. And then the last example of the first half of the list was a discussion about infinite source is not, although when you pick up the utility icon in EasyPower, the infinite source data is already entered in the parameters, and in fact that's not usually accurate when it comes to real-life systems. And the downside is that very frequently the infinite source data doesn't even reflect the worst case situation. So there you want to make sure you get as accurately as possible information from the utility company, and if you have to make assumptions to generate whatever data you use, then the way to guard band that is actually use a number bracketed with numbers that are less than what you receive from the utility. Again, lower numbers generally refer to longer tripping times, which would reflect in higher incident energy. Okay, so that's what we did last time. And for more detail on that, I'd encourage you to look for the video that we put on the website, the first half of this list. So now as we get into the second half, number 6 on my list is working distance. And we find frequently that people use the default dimensions, which are in the tools, which is 18 inches, and not really sure why this is the case other than frequently or usually engineering firms are interfacing primarily with management, and quite often the majority of the arc flash assessment stays with the default working distance. The significance there is the more interaction that the person conducting the study and specifically the people collecting data, the more interaction you have with the maintenance team and the people that actually have to do the work on the equipment, the better the data collection process will be, and the better understanding of what procedures will be conducted in the arc flash boundary. So the example I'm going to show is by using the default of 18 inches. In one case, for a one bus, we come up with a 16.4 calorie rating. And so that 18 inches, the default that's utilized in the calculations, is supposed to be the distance from the arc to the thorax, or the length of a person's arm when you're working on equipment. If I'm poking my head in the only opening, I have to look with my face, look inside a box as I'm making adjustments or taking readings, and that's the only distance or the only area that energy can escape from this enclosure, and my face is supposed to be farther away than the default distance. The fact is I will be exposed to considerably more energy because at that point, an important part of my body is not at arm's length away. So what I'm going to show here is an example of how to utilize custom working distances, and this is on the Arc Flash tab. So let me jump into that example. So here we have a one-line diagram, and I actually put this together as an example for a couple different reasons, and I kind of want to get into those as we talk more about this. I'm going to go ahead and enter short circuit focus, fault all the buses, look at my incident energy. Actually, I'm looking at equipment duty here. Let's look at incident energy, and I see on a couple buses that I have elevated energy, and it looks like I've saved the example already with my default set at 14 inches. So the way that this was done, where these two buses have calculated at a working distance of 18 inches, by talking to the operators, I found that this bus, I wanted to use a working distance of 18 inches because that's what's actually utilized in maintenance operations. So the way this is done is if I look at my arc flash hazard spreadsheet, I can see that my default working distance here in inches for two of the buses is 18, and for one bus is 14. Now where this comes from, if I go to short circuit options, arc flash hazards, the default distance is set for the whole system by utilizing this matrix here, and we're in the 300 to 750 volt range. So we are calculating the threshold of 4 calories per square centimeter with default working distances of 18, 24, and 36. And this is selected and indicated to be calculated for an enclosure or enclosed box as opposed to an open air system. Now where this results are shown, if I expand this plus sign, I can see those incident energy, the default distance, and the others that were selected based upon and the energy that would be provided if we could extend the working distance. Now what I have chosen is actually a different default setting for this other bus, and the way that is selected, if I go back to database edit, go to that particular bus, go to its arc flash hazard tab, I can see that I've set a user specified working distance of 14 inches. Now, one other place to note, I can also override the orientation of the bus work. Turns out if this is not a vertical bus, it may be important that I select or verify that it's either horizontal or into a barrier, because that affects the incident energy calculation. So anyway, because this particular bus is different from the standard, I'm utilizing its bus data dialog box to override the global settings. Now, while I'm here, you notice when I was back in short circuit focus, I started off with incident energy and equipment duty. Well, it turns out I had a question from a customer that says, what should we do to the label if we know that we have a duty violation on a certain bus? We want to warn the operators of that condition, because it's going to take us some time to fix them, to change the breakers. So what we did is, in the buses that were identified as exceeding the duty compliance, we used the device code and entered the word duty here for that individual bus. In fact, we did it for a couple of them. Now when I go back to short circuit focus, fault the buses, look at my equipment duty, you can see I have 3 buses here that exceed my equipment duty. So in the equipment dialog box for each of these buses, I put in the word duty. Thereby, when I go back and calculate incident energy, look at my spreadsheet, go to my labels, now I've customized the labels to reflect special coding for those particular buses. And what that amounts to is I put the red indicator, and this is just a recommendation. It's not anything that's covered in NFPA 70E, but it would be something that I would recommend for the company policy in this particular case. And the way this is done, if I go to my label editor, which I'm now entering, I pick up a standard template and then I save it, and I've entered this text, which I created some new text, typed in the word duty, gave it the red color for the font color, and I made it get conditional. It shows up when the device code from the database has the word duty in it. And so when it's not there, it's blank. So now as I strobe or go through each of the buses, you can see duty shows up on the buses that violate that particular variable. Okay, that gets a little far afield from my example, but just because it was convenient, I wanted to include that. All right, so let's jump back into where we were. So number 7 on the list, misapplication of the 2-second rule. In NFPA 70E, Appendix D 2.4, there is an excerpt that's taken right out of the IEEE guidance, and in essence, to paraphrase a little bit, for greater than 600 volts open air, consider how long a person is likely to remain in the location of an arc flash. If that is likely that a person exposed would move away quickly if possible, 2 seconds is a reasonable maximum calculation time. Use sound engineering judgment. Well, from that, many people take this, and frankly, this verbiage makes me rethink even applying the 2-second rule in 480 volt systems. But there is what's considered to be a 2-second rule now, and it's somewhat, well, I guess I don't consider it to be a rule at all. But there are some people that tend to think there is a 2-second rule, and frequently this is how files will show up as we're talking about them. Let me kind of look for my example. And what we see here is a very large system, and by default in their short circuit setup, they have set 2 seconds as the maximum time for calculations of incident energy in all voltage areas. Now, I'm going to discount 250 volts or less just because that's a different situation. But if we're getting incident energies that are higher, or they're limited by the 2-second rule at 250 volts or 1,000 volts, I frankly would be very concerned about the safety of the system. So let me kind of jump into this and see if I can show you a couple examples. So as a result, what we have is an example here where if I go into short circuit, fault the bus, and so it turns out this number 1 furnace CP is one of the buses that's limited with 2 seconds. And if we just isolate it, we can see that it's 9,000, almost 10,000 amps of arcing current left on its own. Specifically, this fuse would trip in 8 seconds, but by default we've limited it to 2 seconds by that rule, and it's still at an elevated area. In my mind, this is not something, it doesn't behoove me to limit this particular situation to 2 seconds. It's just someplace that I don't think anybody needs to be working on while it's energized, no matter what kind of equipment they have on. Another case that, let me kind of go in and find my example here. And on this particular bus, we have a similar situation where we fault this. We've limited to 2 seconds. In reality, it won't trip for 9 seconds. And again, we're saying don't work on this equipment. I really don't know what type of equipment this is, but it's possible that somebody needs to work on it. The clue here is apparently during data collection there was no display, and so they assumed max trip settings. So ironically, what this represents is not an excessive incident energy. What it represents is an unknown setting on the TCC of the breaker. And so if we look at this and fault it, we'll see that our arc flash current, if I insert this in my curve, is right on this vertical bar. And if in fact I can just reposition the settings for the instantaneous delay or the threshold, we can look at incident energy that's quite civil, and consequently, while I applaud and endorse someone that's taken the conservative position, I guess I would reinforce the fact that we need to make sure this is set correctly rather than have someone work on this with excessive energy unnecessarily. Okay, so that was a long discussion. Hopefully you got something out of that. Let me jump back into my Next example. And that's what's kind of fun about these examples, that they cover several different categories, and it gives me an opportunity to kind of move around as far as the what's in the example. All right, so then that was the 7-second rule. And so here's where that's considered, and that is you can limit the, oh, I didn't show that. Let me jump back into where that's covered. So where that's actually covered in settings-wise is on the short circuit setup page, and by limiting this to 2 seconds, normally these are 1,000 seconds, which means it will never trip. Frequently, I like to leave this set at 100 for both of these and verify what the real energies are before I play with anything that reduces the time. If I do find a bus that it makes sense for whatever reason, the sound engineering judgment says, yes, let's only calculate this to 2 seconds, my recommendation would be not to use the global setting, but to go in and change the settings on a particular individual bus, and rather than calculate this, either force it to a specific value or user-defined time here and use my 2-second setting here. Okay, let's go back to where we were. So number 8 on the list, there's no change in the system. Frequently, people will come in at their 5-year review period and say, okay, there haven't been any changes in my system. I just want you to rerun the numbers and provide new labels. It's like, really? Okay. Why are you doing that? Well, we don't have the means to collect data for an update. Well, is that what that really means? Are you sure? Again, when an engineering team or a management team is verifying the data is accurate, there's a whole lot of risk being lifted off the back of the person conducting the study. Because what we're talking about is, are you sure no fuses were replaced with accidentally the wrong size and for some reason wasn't documented? Are you sure no one tweaked any relays during an off shift and didn't document that? Both of these could potentially reflect substantial modifications, and frankly, utility may change in the 5 years that you've been in operation without telling you. Are you sure that's not in fact impacting your validity and accuracy? And so consequently, I think we're missing the point of doing an arc flash study, because there are ways to, I think, spot check the critical. If the cabling hasn't been changed, the equipment hasn't been changed, I understand that there may not be a need to do a complete ground-up data collection. But frankly, what we're talking about is validation, and there's some key areas that need to be double-checked, and this will essentially vary based upon my specific case or situation. We still see people with labels that have HRC categories on them. 2015 NFPA 70E does not permit instant energy and working distance. Even if you do have incorrect labels and you haven't had time to make the changes, my recommendation is to train employees to understand what the label represents and still take steps and a timeline to replace the labels. And if we look at a real quick example of this, I can show you where this is set up. So again, in short circuit options, when we go to advanced, in the arc flash hazard tab, advanced, with this checkbox here, we show the PPE level, and to show the PPE level, we'd use the older version of NFPA 70E. If we don't want to show the PPE, because we're not permitted to, then we want to show PPE checkbox cleared and NFPA Appendix H3B as the reference. And so that's what will eliminate the instant energy from being on the label, or rather the HRC category from being on the label. And then the last one on the list is understanding or using the main breaker in the panel classified as including or excluding. Frequently the question is, well, why are we excluding it because we don't think it's going to work? The answer is it has nothing to do with the reliability of the breaker. This category has everything to do with the location, the physical proximity of the breaker, and whether or not there's a flash barrier between the incoming conductors and a person working on the hot bus. Very often the most dangerous time of any procedure is when you have to remove the cover, and for some reason you're not prepared to carry the load, or the load shifts because of the extra weight. Having that cover fall into the electrified panel is very dangerous, and the potential to create a short upstream on the main breaker is real, and that's just one example. So consequently, if there's a short that's created there, is a person protected downstream by that breaker? And the answer is no. And if I can get another example here real quick. And so the bottom line, if we're looking at a situation like this, and we open up this breaker bus 2 panel, and we have to make a decision about whether this breaker is included or not. The decision on that is made both at the global level and the local level. If I go to short circuit options under the short circuit focus, my arc flash hazard tab, this pull down box allows me to set on a global basis whether I'm including, excluding that main breaker. And the way this looks, if we fault the bus and look at instant energy, we can see now that this instant energy of 0.5 calories is being controlled by this including the main breaker. If I exclude it and apply, you can see it jumps up to 1.3 calories. So again, the recommendation is to set this global at what the average is, or most of the breakers in the panel are at, and then on an individual bus where, let's say for instance here, the main breaker does have a flash barrier, and we're not exposing workers to undue hazards, so this breaker will actually be included. We can verify the condition of this bus, the arc flash hazard settings can be overridden on a local basis, and for this particular breaker we would include it for this bus. So that's done again on a local in the database edit. For global settings are handled in short circuit options with the short circuit pull down box up here. All right, so that concludes my list, and we're out of time. Real quickly, starting large is a problem for beginning users of the tools. Likewise with inadequate data, recognizing when you have a more dangerous situation or a need to tweak the calculations in a conservative situation below 125 kVA is a concern. Whether buses, and for that matter the bus rating is entered as data, is important when we're doing not just short circuit calculations but also the equipment duty calculations, making sure we're not just using the default infant source parameters, making sure we're considering what the actual working distance is for procedures utilizing each specific bus. Don't be, I think, overly liberal in the application of the 2-second rule. In fact, I don't even like going there. I like looking at each case by case and considering the energy involved. Ensure that you're not shortcutting yourself and your employee safety when it comes time for review, and consider validating the data that has any possibility of changing. Make sure your labels are properly indicating the calorie level. What I didn't explain here is that I may not be able to change my existing labels right away, but I want to train my people as soon as possible that instead of looking at the HRC category, I want to be looking at what the calorie level is, because the old labels usually have working distance and calorie rating, and that's where I'm going to be focusing on PPE selection in the future. And then include or exclude the main breaker is very often mishandled, again in part because the data collection may not have considered what the condition of the panel is as we were doing collecting the data. I appreciate everyone for attending. By all means, check out EasyPower.com, because we have the regional training sessions scheduled now for the next 6 months. Just a note, we're going to start alternating webinar weeks. Every other week we'll have a Tuesday webinar, and then alternating in between every other week we'll have Thursday webinars. We have a new addition to the knowledge base under EasyPower.com support knowledge base, and it has a growing list of frequently asked questions that are very much more technical depth than FAQs having to do with sales related questions.